So let's start. Dirk just turned on the recording, so everything you say will be recorded now. And also welcome to people at home. Hope you're there and listening. Well, these are also free. Like this is not no extra costs here. Heel lekker nou, ja. Het is niet helemaal free. Ja, precies. Heb ik een beetje het gevoel. Alsof ik niet tegen de horizon sta te gillen. All right, welcome. Is this the group so about? Is this the amount of people you expect? Except for the 10s online? Or 8, 9 online? That's about it? All right, let's start then. So welcome to another lecture on the Biomedical Optics lecture series. And it's my pleasure to talk to you. I always have a nice role in this lecture series, where I'm allowed to let you think about all the ways you can use the toolbox that you have been provided with up to now. Dirk Faber's all the theory about scattering, about measuring quantitatively, about measuring in very complex turbid media. And I'll just give you a little flavor of what you can do with this knowledge to really make it work in practice. And practice for me is not like biomedical optics, medical only. Some people know this, but I'm also involved in the forensics section. My chair at the AMC is forensic biophysics. So in the group in which I work, we tackle both forensic problems, and forensic meaning, well, for the forensic chain, to find the truth, and medical problems, so medical applications. So these two are very similar, as you can see. Fundamentally, they're very similar. You can use many of the same techniques and the same theory for both applications to develop these applications. But that's a bit of my role. And today I will tell you something about spectral imaging in forensic applications. So we do this spectral imaging, for instance, to look at blood on crime scenes, to look at spectral signatures of blood on crime scenes, first to recognize blood or to see when it was deposited. We use spectral imaging to visualize wounds on victims. It can be living victims for child abuse, domestic violence, or dead victims for strangulation, for instance, these subdural hemorrhages, or like accumulations of blood under the skin, for instance. We can use spectral imaging for that. I'm also using spectral imaging for medical applications, for all kinds of dermal diseases. I'm using spectral imaging for vegetation research, so to look at the vegetation that grows above a grave versus next to a grave. That's also same device, same theories. So this spectral imaging is a very versatile tool that you can apply in many of these applications. The only thing is how to get useful information from the things that you measure. And that's of course something that you've heard by now. You have your toolbox from that. We need to know a little bit more about how light behaves in different materials to understand why you get certain signals when you have certain molecular changes. So that connection can be made using the theory that, well, by now you probably have. Other thing that I will talk about is fluorescent diagnostics. That's more the biomedical application again. And that means using both intrinsic properties of cells and fluorescent properties of externally given contrast agents to humans to find tumors in the body. And that's fluorescence diagnostics. And if there still is time, I will go a little bit into photodynamic therapy. And this is the use of, well, can also be an internal, but usually external photosensitizers, which are molecules that you can excite. I don't know if you've already had something about photodynamic therapy. A little bit. Photosensitizers that you will administer to the patient that will accumulate preferably in the tumor, in the pathology that you're looking for. And in that way you can better image it using, again, fluorescent diagnostics, but if you apply more light, there's a generation of singlet oxygen, and then you will kill the tumor. Yeah.
This is not the same as, say, bringing in a radioactive agent in order to diagnose the tumor. This is exciting something, bringing it into the body, that it hopefully accumulates in the tumor, and then you image the light that comes out.
Yeah, but the excitation will be during the visualization. So the thing is there, you're not exciting it beforehand. You just administer, for instance, a photosensitizer which will accumulate in the bladder or in the esophagus. And then you go in with a probe, do the excitation, and measure the fluorescence at the same time to see if you get different concentrations on the vessel wall or on the esophagus wall or in the bladder. And if you then immediately want to treat, you can also use the properties of the photosensitizer again to give it energy. It will go to a higher state, but not go back and release light in the form of fluorescence, but it will transfer its energy to an oxygen molecule that will generate singlet oxygen, and that's a reactive species that will kill the cells. So that's like a see and treat kind of thing that you can do with optical techniques. And the disadvantage is, of course, that you can only treat at sites where you can, that you can approach with your excitation light and what you can image with your scope, for instance, and it will not go deep in the tissue, your excitation light. So to activate photosensitizer. So usually photodynamic therapy is applied in intraepithelial tumors, which means in the slimy layer on top of organs and in the esophagus, in the bladder, in the uterus, and those kind of things, where you have very superficial tumors, which you can reach with a scope and your light source, and then you can treat it. And that's the photodynamic therapy. These two were actually part of my PhD thesis a long time ago, and after I studied physics. I went into Fluorescent Diagnostics, photodynamic therapy of gynecological tumors, and some way I got astray and ended up in the forensic corner, but these things happen. And basically it's all the same. I'm using the same scope, same technique, same theory, basically, to analyze the signals coming from either a dead body, a blood stain on the wall, a tumor in your abdominal cavity, or whatever. So that's all what you can apply. Well, the theory you know by now. I think my camera is a bit foggy from the rain I just went through. Sorry, guys at home. Guys, people at home. Yeah, these are several pictures that we have. This is the crime scene at the Arista site. That's a burial site that we have at the AMC. So we can bury people and then look at their decomposition process. We can do all kinds of measurement on that. So here, that's on the AMC ground. And then also we use the hyperspectral imaging again to study the vegetation on top of the grave versus next to the grave. And we also study the change in environment, which we call the taphonomic footprint, with our spectral cameras. Whereas we do fingerprint research, how to get best fingerprints using intrinsic properties to enhance fluorescence or to attach some contrast agent to it, or we look at the different components that you have in your fingerprints, also with spectroscopy. We look at the age of the fingerprint, when it was deposited, just that's useful information for forensics, and everything you touch and we can analyze, and there's information in your fingerprints that tell you something about your drugs, the alcohol, things that you consumed. If you're a vegetarian or a meat eater, we can study that. All kinds of diseases. So that's all already there on your desk. So we can study that and make kind of a profile of the donor. And using intrinsic fluorescence properties, we can estimate when it was deposited. Yeah.
So really in the fingerprint, the pattern itself, or more what is deposited along with the fingerprint?
Well, for us, the profiling is more important. So the stuff that's deposited. For identification, we need the line structure, but we can also get an enhanced image of these ridges using staining that we can selectively apply on these ridges. So it's also for enhancing fingerprints, but it's also right now they're just studied for their patterns and for identification. But there's of course a lot more information in that if you study all the chemical components, and we can also do that with fluorescence imaging and labeling and those kind of techniques. Dead bodies cooling down, the crime scene stuff, the hands, autofluorescence, the picture from the grave. On Arista, and we studied also the whole decomposition process. And for that, we do 3D imaging. So a little bit of spectroscopy, spectral imaging, forensic applications, and then we go more clinical, as I just told you. And this is our toolbox again. You've heard all about light transport, but it's all a bit, I can imagine, it always was to me a bit abstract until you start to have an application and start to think about an application. So just a little recap here. For imaging, of course, we can use the intrinsic contrast. Anybody have an idea of what it is? It's an OCT image, yeah. Of what?
I would guess a bit of skin.
Skin?
Because I think I can see a sweat duct.
Yeah, the spiraling down sweat duct. And how do you get the contrasts here from OCT? What's the contrast?
The upper skin and the lower layers of skin.
Yeah,
so you see the, I don't know what that's called, the horn laag. I don't know what it's called in English. At the very top, then you go the opperhuid and then the layer below that.
So stratum corneum, and then the epidermis and dermis and the layer between that. You can see these. What's the optical property that we're looking at here? Yeah.
Refractive index.
Well, the refractive index is the basis of that's the basis of what we're looking at here. But what is OCT typically looking at?
Interference.
Different phase.
No, it's the interferometric technique, but it's the phase. Why is this more clear than the part below or the part above? What's the optical property that is behind there? I mean, what are the 3 optical properties that you can have in tissue? This is what we will do. So you have heard 1,000 times these optical properties.
Absorption, refraction, and scattering.
Scattering. So what's OCT looking at?
No refraction. Because it looks at the way. It looks at the amount of light that is reflected and contrasts that against a reference sample. It looks at the interference between the sample and what it will detect.
Yeah. And scattering is one thing. And if you have, for scattering, of course, you need different refractive indices between the different components, the intercellular fluids in the cells, the outside of the cells, mitochondria, those kind of things. They all have different properties. If you have different refractive indices, there will be scattering. It's often called, well, a lot of times it's called scattering, while it is diffraction. It's just a change of direction, basically. So, well, it is refraction in a way. So both right. I'm just a peacekeeper here. And it's also refraction and direct reflection, Fresnel reflection from the top layer, of course, that you will get in your system. For the rest, it is remittance from a low order scattering, so just 1 or 2 times scattering, and then back into the system, which indeed will be recombined with a reference arm and form some interference pattern, and that will create your image. So here it is many times, but that's the way you can apply your knowledge of tissue properties and turn it into an image. What are we looking at here, you think? Sorry for the people at home. I don't know. Yeah.
The heart?
No.
Lung?
No. That will be a very clean lung. Somebody from a rural area somewhere there. Sorry? No, it's larger than that. It's the brain. So there's the dura, which is the layer of vessels that is just on top of your brain. So it's called the bony part is removed. It's called. You directly look on the brain here, and of course, then for the surgeon is the question where to go in there to just see where the pathology is, so how extended it is. Because brain surgery is very conservative, so you don't want to cut too much away. You always leave some margins there. It's never clean. It's never clean surgery. Because as a surgeon, you really want to know where these boundaries are. What's the delineation of your tumor? And for this, we injected this ALA, aminolevolinic acid, which was turned into protoporphyrin, and that is highly fluorescent. And the fluorescence accumulation, that's what you see here in this brain. So now the surgeon knows where to go through the dura and perform the surgery. Well, that's with light we can heat things. I will not go into that. Induce photochemical reactions, so that may be the second part. And the spectroscopy is one of these things that we will look into. You all went through these different forms of spectroscopy. Low coherence, yeah, like OCT, sort of. Raman spectroscopy is known, of course. All the schematic energy levels that were drawn, probably. Fluorescent spectroscopy, reflection spectroscopy. Right. So just for some forensic applications, and they will be later on. We go more in depth for the theory. There are some typical forensic questions that we're asked and that we can answer using the toolbox that we have in our Biomedical Optics section. So for bruises and bloodstains, it's very important to see them. What's the other important factor here? Don't answer. So what do you want to measure on bruises? So that's the when they were inflicted, or yeah. So that's the that will confirm or reject the story if you know the time when things happened. Now you can put things on the timeline. If you have blood stains on the crime scene, you want to know if they are related to or have something to do connected to the crime or not. So there can be old blood stains and new blood stains, and so the timing that the aging of these biological traces. And here we go back to the tissue, biomedical optics, is super important. We can do that with hyperspectral imaging or diffuse reflection spectroscopy, some other techniques that you can apply in different forms, different ways, with cameras, with fibers. Or use fluorescent spectroscopy for bloodstains for the plasma, which is high energy fluorescence. And this is an example of what we're looking at. Spectroscopy is basically seeing colors. And here you can see the aging blood stain, which just changes color. But the eye is not super sensitive, and if you can very accurately measure the changing color, we can of course say something about the time the blood stain is deposited. And that's something that we'll go into later. Bruises. Here you can see the typical bruise with some outside and some inside colors and more colors on the edge. So is this a young bruise or an old bruise?
Probably an old.
Why?
Because a young bruise would typically be redder.
Redder. Yeah, that's it is more hemoglobin, more oxyhemoglobin, and that's red, or more hemoglobin that was freed from the blood cells, because it will be in contact with the skin, then the blood cells are broken down, and then you will have free hemoglobin in your skin, and that will just diffuse upwards towards the skin surface, and then you will start to see it. So that's red, and then there's a conversion to what's the typical color that shows up then?
Bilirubin, right? It's sort of yellowish brown.
Yeah, yellowish brown bilirubin, and that's something. All these color changes can also be studied because we know these spectra. We know how we can correct for the properties of the skin, so we can have some timeline in there, and then calculate it back to the moment this person was hit. So there's all kinds of body fluids that we're looking at. Body fluids are of course also very important in the forensics. These are often found at the crime scene. There can be semen, saliva, sweat, urine, everything that leaks out of a body. You can find on the crime scene, and maybe some sort of evidence, may contain some sort of information which you can use to know something more about what happened in the past. So these body fluids are from itself very fluorescent, which is a way to find them. But if you start doing spectroscopy on this fluorescent signal, then you can see also some information about the age of these body fluids, which is of course very important if you want to study again the timeline. Identify the fluids, study the timeline, and find them. And again, fingerprints we call also body fluids, and that's also what we do here. Yeah, the other thing here is bones. Tristan is working on bones. Bones are also highly fluorescent. And the question here for Tristan was how long were they exposed to a certain temperature? Because then the chemical composition changes, and that will mean a change in fluorescent signal as well. So using fluorescence imaging and spectroscopy, fluorescence spectroscopy, you can say something about the time the bones were exposed to fire. That's also important forensically, because if you use some kind of fire accelerant, the temperature of a typical fire will be much higher compared to when things just start in some electricity box or something. So there will be different temperatures. And that's something that we will study on the bones. For the rest, we study with fluorescence where we can best sample these bones for DNA. So what's the most viable part, basically, left of the bone, if you find a bone. And also if these bones were, say, damaged, we want to know whether it was before death or after death. So that's the other thing that can be studied with fluorescence. Because then there will already be some healing process in these bones, and they will fluoresce differently from some scratch marks or bite marks that were caused later, because then there's no regrowth of the bone material. So that's also part of the study. And then with the Arista field, well, that's our graveyard. And here we do thermal imaging, which is also spectral imaging, I'll show later. So we go far to the infrared, and there we can study things related to temperature. And there we look at the heating or the warming up of the soil when, for instance, the sun comes up. And the soil, the heating of the soil, the kinetics will be different when there's a body in there compared to the pure soil. So you start to see contrasts when there's a body in the ground. That's something that we can do with thermal imaging. We work together with the drone team of the police. So we equip the drones with spectral imaging cameras, with thermal cameras, and with LiDAR, which is the ranging, so you can do topography of the field. And there we can well, work on that. And we do all kinds of 3D imaging with a technique that's called photogrammetry. And you're all able to work on all of these projects with these toolbox that you have, because they're all based on generating some sort of emission, which can be a diffuse reflectance, can be spectral reflections, can be, I don't know, fluorescence or anything. And then, well, catch it with a camera somehow, capture the signals, and then understand what's behind the change in signals from the incoming to the outgoing signal. And that's tissue optics, basically. That's something that's totally in your head right now, probably, after a couple of classes from Dirk. It's very fundamental, very theoretical, probably, which is the toolbox that you can nicely apply for all of these applications. So when you're looking at all these slides with theory and more theory, you must always think about, what can I do with it? Can I use this for some application? And suddenly this lecture will be much more fun, because thinking of all these applications, it's like, hey, how can I use scattering properties? How can I measure these scattering properties? What's changing here? Maybe there's some absorption change, some scattering change, some molecular change. Maybe I can use it. How do we do that? Well, applying some light transport equations, and then do some analysis of your signals. So it's your toolbox. It's not, your final goal is not here to prove that your toolbox is okay, but that you can think one step further. And that's how to apply it, which is higher in complexity, probably. It's something that's really necessary in the later stages. So spectroscopy is, we're also working together with the Van Hoff Institute, and Van Hoff Institute at Science Park of the UvA. They're really in the analytical chemistry corner. And usually what the analytical chemists do is they have a very complex sample. They do some separation steps first to just, well, get all the individual components separately, and then start doing analyses on all these individual components with super advanced mass spec stuff. Spectroscopy, that's the optical technique. For that, you can both analyze individual molecules, but you can also analyze very complex measures. It's usually a very coarse technique, but it will give you a very direct idea of what you're looking at. And this is the thing that we're looking at. So chemical analysis, interaction of light and matter again. And the spectral response is very material specific. That's something you need to know. all the small changes in their chemical or absorption you will see in your spectra. So you have to analyze it very carefully. What you usually for that is uses some light transfer model. You need to know what's happening with your light in order to correctly analyze it and interpret. So, well, you have your intensity. This is maybe a spectrum that's coming out. And if you have your input spectrum, your outcome spectrum, the very simplest trick is, of course, Lambert-Beer. And then you will have your absorption property of your molecules. And that's something that's straightforward. But if things are more complex or layered, you need to know more about light transport in turbid media. I will talk more about spectral imaging, which is basically a combination of the spectroscopy you're probably used to, which means it's one beam through a cuvette and then the measurements, and then usually a cuvette with some solvent only, and then the solvent with your molecule in there, and you compare the two, and then you have your spectrum. And with spectral imaging, it's slightly different. We're combining spectral and spatial information with a camera, and we do that for remote sensing, of course. The spectral cameras will capture not camera or your DSLR camera, which has RGB, but the spectral camera typically captures 200 to 1,000 images per scene. And these images all have information about one specific wavelength. So with spectral imaging, you're building this spectral cube, we call it. And this cube has like two spatial axes and one wavelength axis. So for each pixel, you can analyze the reflectance spectrum. Every pixel has that information, about 200 points in the spectrum. You can do that for every pixel. So it's a great tool to study larger surfaces, which you have in patients on the skin, in the bladder, in the larger surfaces, instead of going around with your optical fiber. And you have all the spatial distribution of certain components, which also gives you information, diagnostic information, or information based on patterns of your traces that you can also have with, and each pixel will give you some sort of a spectrum. That's the trick, that's spectral imaging. For our techniques, and we will look first at the forensic application, we'll look at the identification and age estimation of bloodstains, of bruises, and some other wounds and forensic traces. Sorry, you'll see the whole lecture again. For medicine, but also for forensics, of course, it's important that you're not compromising the trace, you're not interfering with the trace, there's no contrast agent necessary, it's non-destructive, can be very fast, mobile, and versatile. So you can do it, apply on many different kinds of materials, and that ranges from people with a tumor to forensic traces on walls or those kind of things, to paintings. We're also doing the Nachtwachtproject at the Rijksmuseum, so measuring the pigments in these paintings. And it's basically a very generic technique with which you can do a lot of things. So it's the hyperspectral imaging. And we have the variation, and this is our toolbox. The wavelength scale going from 200 UV about to visible part here, 750, near infrared 800, 750 to 1000, shortwave infrared about 1000 to 2200, mid infrared depending on in what industry you're working, and then larger wavelengths. The IR we can all use to image certain processes, to image traces, to image pathology in patients, and this is basically our toolbox, which will create our contrasts. We're going to do forensics now. So simple photography, colors, just RGB, 3 colors, visible spectrum will give us a normal image. And the contrasts here are again determined by absorption, scattering, but then the visible range, so it's very comparable to what you can see with the naked eye. If we go more to the infrared photography, then there's another contrast. The color of the clothes that's basically gone because our clothes are designed to have a color in the visible range. So if I would image you with a near-infrared camera, you would always all be wearing white, and only the smudgy parts will be visible as traces, which is super useful in forensics. because we encounter, a lot of times we encounter black clothing or black sheets or anything. And using that specific wavelength range here, we can get rid of the color, the dye that's used for this clothing. We can still see our interesting forensic traces. So that's playing around with the wavelength. Thermal imaging, of course, that's the IR. Every body, every material, every object that has a certain heat will send out radiation. Planck's law, you probably heard all about that. This is just an infrared imaging camera, and there's a kind of conversion from this infrared radiation to some thermal image. But then if you have the properties right, it is really a thermal image. Then you can see the temperatures of the body. But also different traces, different contrast can be obtained using these cameras. Because the thermal imaging, if two objects have the same temperature but a different emissivity, if you still remember something of the BNOS, there's an emissivity term in there, then you will see a contrast with using these cameras. There's no temperature difference, but you can still distinguish different materials which may be non-distinguishable using the eye, but using these kind of cameras, you can still see the contrast. So also very good for different contrasts. So where the Rgb imaging, and here we go from normal photography to Rgb imaging, you use your three colors to create your color image, and using spectral imaging, you have your 200 colors in a broad wavelength range that will give you your spectral cube. And the spectral cube we can use to chemically analyze every pixel that's in there. Super cool tool. Up to like 5 to 10 years ago, this camera was huge. You needed to have like 3 physicists running around taking care of the cables and the laptop and the rotating tripod. We were using cameras that were usually attached to airplanes, which were flying over forests and seas to capture this information. But now we scaled them down, or they were scaled down by the industry, basically to a kind of DSLR size camera that you can just put down on the crime scene or in the OR or in some other room that will capture automatically this hyperspectral cube from your from the surface you're interested in. So that's really within reach now for all kinds of applications, and that's why it got extended to forensics, to medicine, to art, to food safety. So here you can capture your spectral cube. You can still recreate your color image, but you can also have your spectrum at each individual pixel. Cool, eh? So this is 2 peaks here. They are typical for oxyhemoglobin. There's a little peak here, which is typical from the breakdown product of oxyhemoglobin. So from this spectrum, we know it's blood. And we know it's a couple of days old, because this little peak here is only present in blood that's somewhat older than fresh. So you have an immediate chemical analysis. For bruises, so now we're going to wounds, we can also apply this. This is stepping through the spectral cube. So here is wavelength. Each of these images in the spectral cube represents the reflectance of a certain wavelength. And here you get all these images. And this goes from 400 nanometers blue to 1000 nanometers in the near infrared. So beyond what the eye can see. With that, we can carefully study bruises to see if we can recognize when they were caused. So starting again at 400 nanometers. It's a bit light here.
Switch off the.
Yeah. You have to run.
Switch off the lights over there. Oh, there's buttons over there.
Thanks. So at short wavelength, there's a very high peak of the bilirubin. So that's the greenish, yellowish, usually a circle around your red stain. That's the breakdown product of hemoglobin. And that's the first peak there. And that's about at 4 something or 20. It's very vague, but you can now already see some delineation of where this bilirubin is went to. Oh, a little bit difficult here. If you have it go further to the visible area, this is where hemoglobin starts to absorb. So now you have the areas where hemoglobin is visible. If you go beyond the 600 nanometers, there's very little absorption of hemoglobin. And here you start to go deeper in the tissue. Longer wavelengths is deeper penetration in the tissue. And here you start to see the watery components in the tissue. It's very hard to see on the screen now, but it's poor. So from this, we can get the distribution. We can identify all the different components that are involved in the clearing of these bruises. We know how fast the conversion is from hemoglobin into bilirubin. And if we can determine how far this healing progressed, we can calculate it back to the moment that it started. Well, at different points in the whole process, in the healing process, you can see different components more clear. And in this case, you see a very high peak here of first peak of hemoglobin and bilirubin. And that's something that you will see throughout the healing process. Chat. You have to. Totally makes sense.
You just stop the screen sharing.
Yeah.
Back in control. Click out of your presentation.
I know. Let me do the video filters. Usually I'm presenting from terrible basements, children's rooms and stuff, so I have to blur the background to make it somewhat okay. At least to give the people the idea that I take them seriously. But for now it's super annoying, I agree. So that was the chemical analysis of one individual pixel. If we separately look, what's important for imaging, no matter whether it's diagnostic or whether it's for forensic, we need contrasts. And contrast means at this point there are different optical properties than this point. It can be absorption, can be scattering, can be fluorescence, compared to some background, some surface that the trace, the pathology, the bruise is on. So with spectral imaging, you can just play around and look through the spectral cube to see where you get maximum contrast, which is impossible to do if you're studying your pathology, your skin, your wall with the naked eye. Yeah?
I don't think you're sharing your screen yet.
No?
No, I think you're...
The bluish thing is not... Oh, it's
you're
one.
In the selection phase. You're in the phase of please select your screen. Yeah, there you go.
I'm always a phase behind what I think I'm in. Very opmerkzaam. So what we need are contrasts, and that's basically differences in optical properties, difference in scattering, difference in surface materials, roughness, absorption, fluorescence. And with these spectral imaging, we can just scroll through the whole spectral cube to see in what wavelength range we can find the best contrast. What do you think for blood it is? Do you still have the idea of the absorption spectrum in blood?
Yeah, there was this one wavelength where you could see you could see very clearly the contrast between hemoglobin and bilirubin. Something in the 700s.
I think you're referring to the oximetry lecture.
Oh yeah, no, that was, yeah.
And that's oxyhemoglobin versus deoxyhemoglobin.
Yeah, that was something else.
Yeah. And for blood, but you know the typical absorption spectrum, right?
Yep.
So where are the typical absorption peaks?
400.
There's a huge one. Yeah. And where's the second? So what color is the eye most sensitive to? All super practical questions, yeah. But it all has to do with spectroscopy. Right?
Green, no?
Green, yeah. So in the green part, there's a strong absorption of blood. Very at 400 nanometers, there's a huge absorption peak. And then after 600 nanometers, it goes down. So you would expect something of between 5 and 600, maybe there's a large absorption. Because for these very short wavelengths, also the background materials will have a large absorption usually. So this is a fingerprint in blood on a red table, nearly indistinguishable by the eye. And at 450 nanometers, it's also hard to see. (500 nanometers, that's just before the absorption peak of blood. And here you can see that the blood absorbs more light compared to the surrounding materials. So the substrate it's on. 550 nanometer, that's nicely in that absorption peak between 500 and 600 nanometers. The oxyhemoglobin has these two absorption peaks at 520 and 577. So here you can see a nice contrast. At 600 nanometers, contrast goes down because just simply the blood absorption gets less. And the substrate, well, gives back a lot of light. And it's more equal than here at 650. So what you have is a very high contrast image, and in this case it's just a fingerprint in forensic context, but the same with bruises, same with tumors, pathology. If you're at absorption peaks of blood, then you will get maximum contrast also when there's a tumor. And here you can just take one pixel, look at the spectrum, and here you can see the two absorption peaks of blood of oxyhemoglobin. And here's some other peak, as I just explained, from the breakdown product, and it will give you the idea of this is blood and with a high contrast image. So a super useful tool, just using all the optical properties that we know of, that you've heard about and know by now, to get this very practical application, which has a huge forensic value. So very simple theory, high tech, but that's industry. And then we get this nice application, and we understand it because we know the optical properties of biological materials. We've been fed along many of these classes. So that's the hyperspectral stuff. We can also have multi-spectral imaging. And that's simply putting a filter in front of the camera and having it rotate very fast. And then you can just put in filters in and out, the colors that you like, select. And then this camera will make 8 images very fast of these wavelength bands. And that will also give you the opportunity to study the processes. Because if you just want to measure blood, you want to measure this peak, maybe something here between here, maybe some background, 850, some water peak. So specific for the chromophores that you're looking at, you can select your wavelength to make it a dedicated tool for a specific application. And for that, you need to know, again, what's creating my contrast? Contrast is the key. What's creating my contrast? Do I need to look at scattering? And I don't want to be bothered by absorption peaks, so I will go to this area here. Is my pathology, is my tumor contrast that I want to see, is it created by blood, for instance, which is usually the case in tumors, because there's a higher density of blood vessels usually when a tumor starts to grow. So blood is usually your contrast agent if you want to study tumors. Then you can use these kind of properties. So this is the huge peak at 400, between the 500 and 600 second peak. There's the scattering. Is my interest water, for instance? Then you can go to longer peaks. Or even, is it more proteins? Then I go to much longer peaks even. So you can play around with the wavelength to create the kind of information that you want for your application. That's key. We know these properties because we have measured all the individual components. We know the interaction. We know what effect a certain change, molecular change or structural change will have on your optical signals. And then you can design your technique around it. So here we were interested in the bruises. So we designed that camera with these wavelengths. And that's because we know what we want to look at. We know what gives us our contrast. And that's key for this application. So here again, spectral imaging, kind of a white light image as you would see it. 450, not so much, 480. You get closer to the blood absorption, but there's still a flank of the bilirubin peak. This is the hemoglobin. You see a different pattern. If you look at this, which is much more don't know if you can see it by the way, but there's a little island here and some things around it. Of the hemoglobin, this is much more diffuse. This is the bilirubin, 4 times smaller molecule, so diffuse is much faster. And here you can go more to the 620, where you can see the outs, but that's a bit of the end of the absorption peak. And here you can suddenly see the vessels and a larger stain. Why is that? What's the advantage of 850? Yeah, and what's the other advantage? Deeper. Yeah. So also you have to take into account the penetration depth of your light. And that's, well, all scattering laws, and you've had them all. Probably you heard all about that. So this is Rayleigh scattering, very strong wavelength dependency, where the highest scattering is at shorter wavelengths, very much lower scattering at the longer wavelengths. So with this, we're also looking at different interrogation volumes, picking different wavelengths. We're also looking at different depths, and you get different kinds of information. So by making this one scan with these 8 images in, well, a couple hundred microseconds, we have all this information, chemical information, depth resolved information, that we can use for diagnosis or to say something about the process that we're looking at. So that's all the toolbox that you already have somewhere there. And well, part of our department is working on the technological developments. This is in the year 2000 when we were working in the gynecological tumors section. And this was our spectral camera, which is like this, huge. And it had a water-cooled lamp that is a mercury xenon lamp. There, behind there. So 2 cables going to the tap, a lot of noise. 2 filter wheels selecting the wavelength of excitation and emission. A water-cooled camera with a large fan there. And that was for a very subtle diagnosis in patients that were in unfavorable position, so to speak. And we came in with this totally intimidating device, so it was not practical at all, but we got some very good results from it. And now, 2009, we went smaller here compared to this, and now we have the DSLR camera. Yeah, the CSID Hague. Yeah, it's not my idea. But at some point, the Forensics, Netherlands Forensics Institute launched a project which was called CSID Hague, with a very fancy promo movie attached to that. And they were there just to develop new techniques for capturing the crime scene. So imaging of the crime scene, capturing it in 3D, capturing it with spectral cameras, thermal cameras. And during that project, we developed a lot of techniques that, well, we developed this dedicated crime scene spectral camera, which is just a box with the camera in there, the computer, the touchscreen, the storage, everything in there. And with that, we could just go over the crime scene without cables, without laptops, without the physicists that were necessary. It's basically all the same. It's just a nicer box. And here we get some other thing, well, the techniques behind it. Yeah, this is not so super important, but this is the end result basically. Push room imaging. So what you usually have when you start working on your signals is a signal that's very clean. You can just do your light transport theory. You can do the diffusion equation, or you can do Monte Carlos or anything. But before that, you need to have a signal which is clear of influences by the device, the geometry, by light source properties, by the camera properties. You just need to get rid of that out of your signals, of course, because you just want to analyze the signals and the changes in the signals that are caused by the things you want to look for. So for our data processing, we need some calibration. We need spectral calibration, spatial calibration. These are the different steps that we need to take. Because the spectral calibration is, well, what kind of light source are you using? How much of each wavelength is in there? So your I0 basically, light going in. You need spatial calibration. Do you have like homogeneity in your illumination field? Is it all the same intensity at all sites? So you need to do also your spatial calibration. And then you have compensated for light source spectrum and the sensitivity of the detector and the optical transmission of the system. Then you may need to do some spectral pre-processing. Now we'll go back into that later. Maybe there's a different distance between the different objects that you're looking for. For instance, if you have an arm, it's very curved. So this part is much closer to your camera than this part, and there's an angle that you need to compensate for, because they may give different signals while having the same composition. So we need to have some algorithms for that. That's the spectral pre-processing. There are many of these techniques for that. Many have been described in more computational imaging papers. Smoothing, offset correction, normalization, mean centering, SNV, all kinds of things. We'll look at them later. And then we need to do the spectral analysis. And you've been working more in this phase of the whole process by looking at the signal. What was the light transport responsible for such a signal? Here we can, the different components, for instance, present in the hypercubes. As I showed you the hemoglobin, the bilirubin, their concentration, maybe the spatial distribution. You can have like a whole cube full of spectra, two spatial axes. And you can compare that to other spectra for classification. You can say, okay, what's resembling this? Then you get a kind of classification of the different objects in your image. Or you can do a spectral mixing, and that's really analyzing the spectra to identify the chemical components in the, to identify basically the components that contribute to your absorption. That's basically the phase there. And then depending on the user, can be a doctor, can be a forensic CSI, can be somebody working in the art field, can be anybody. And you need to say something, what's the distribution of the components, or what's this value, or that's very depending on the end user, of course. And the path length problem is not solved in these steps. What do you think I mean with that?
Is that what you described previously with your, that you have a curved surface, but one point is much closer than the other?
No, it is related to that, but it's not the same. It's not what I mean here. So how can you do quantitative spectroscopy? What kind of parameters do you need for that? If you take the simplest form of spectroscopy, what are your inputs for calculating the specific absorption at a certain wavelength? It's a long sentence, but what do you need for that? This is an object, and I want to measure the absorption coefficient of this object. What do I need to know?
What light goes in, what light goes out.
Yeah, that's first. And then what? What do I do with that?
Comparing the two.
Sure. Yeah, what's in there? Times? Concentration and path length. Yeah. So in order to do quantitative spectroscopy, we need to know how much light goes in, how much light comes out, or goes in, comes out. And we need to know the path length. And then we have the mu-A, we've heard a lot about, which is, of course, the absorption coefficient, which in a certain concentration range is the extinction coefficient times the concentration. That's mu-A. So it's mu-A times the path length. There's a natural logarithm between that. So the natural logarithm of I divided by I0 is path length times the mu-A. Or I divided by I0 is the, yeah. Well, so there's a minus involved then. There will be a minus, yeah. So that's the path length thing. And if we measure a spectral cube, as I just told you, we measure different volumes for each wavelength because the path lengths are different. The optical properties are different. And we want to measure the optical properties, but we have to know the path length. But the path length depends on the optical properties. There you have a problem. Error. So then we can ignore the whole thing and go more to diffusion equations. But then you require your volume to be What are the requirements for the diffusion equation or diffusion approximation of the transport equation? Still remember that? You probably had it somewhere. Did you have the diffusion approximation?
Not that I can remember.
Okay. Well, there are several ways to describe the propagation of light through medium, or to estimate the optical properties from your light distribution. So if you I'll see you later. So if you have a slab of material and there's no scattering, you can just shine light here, which is the I0, which goes through. Here you get your eye. This is the thickness, and then you can just do your line of beer based on this. If there's scattering, you can solve that, not really, but then the light will be scattered, path length will be much longer, and you can kind of compensate there to compensate the extra path length by introducing a path length factor, differential path length factor they call it. But you need to estimate that, and you can, so that's hard. But what you can also do is to assume that this is a very large medium. This is large, this is optically infinite, so to speak. When there's scattering, you shine your light in here, light will be diffused, and there will be light here coming out, here coming out. So there will be a decrease in the amount of light as a function of distance from the source. And the attenuation as a function of distance to the source is caused by the mu A and the mu S. So there are certain relations. If you can fit this attenuation or the decrease in intensity as a function of distance to the source, you can get your optical properties out. And that's called the diffusion approximation, where you assume that all the light that is in here is diffuse, it's diffusely scattered, so scattered so many times there's no directionality in here. And this is a kind of a diffused cloud of light from which the intensity decreases as a function of distance to the source. And if you have that situation, if you assume that you're infinitely thick medium, and you have a homogeneous like cloud of light, so to speak, scattered everywhere, then you can describe this with the diffusion approximation. And this will give you your that's also a solution. So then you don't have to worry about path length anymore, but you're just assuming a diffuse field, and you're considering or looking at the function of distance to the source as the problem. So that's the path length problem that I'm mentioning here. No comments? The whole screen here is participants at home. So just to work a little bit on the first part, we'll take a break first, or no worries. We'll take a break first. Just a little bit on the first part, and that is the influence of the curved surfaces that you will have on the skin, on the organs, if they're curved like this. On the esophagus, it's a tube kind of way. And the signals that you will get back from your surface, if it's curved, if there are different distances to your detector, you need to correct for that. Now we'll slowly go through that list with some examples, and then the fun part will be back, and that's the application part. But this is just a matter of dealing with the spectroscopy signals. Shall we take a short break? Yeah? 10 minutes break? 10 minutes enough?
Yes. Weet je nog intense gewoon zien? Ja, maar er wordt zo nog een foutje in. Want als je bij
So whenever you want to image something and you have some curved surface, which you will have in many applications in the medical field, if you want to study some body cavity, somebody, I don't know, some also skin, like for instance, again here, the weer op dingen gedrukt. For instance, the bruise in a very curved surface, you may have the same composition here compared to your center, but it will totally turn up differently in your spectra. So you need to correct for that in some way. Another example, or you can use all these spectral preprocessing methods there. And part of your signal will be specular reflections. That's also the case in every form of spectroscopy, whether you do fiber spectroscopy or with cameras or fluorescent spectroscopy. Usually there will be some spectral or specular reflections. And how much will these specular reflections, what's the cause of these specular reflections, you think? Why do we have specular reflections? It's the first boundary between air and something with a high refractive index. That will give you specular reflections. If something is very straight, that will be like mirror. If something is very rough, if there's a surface inhomogeneity, if there is like very uneven, then you will get this more diffuse reflectance. Now this reflectance will be in your signal. What will this give spectrally? Spectrally. No idea?
Maybe all the colors. Expect all the colors.
Just the same colors.
Yeah.
So no information of your object, right? It will just give you an offset, basically. So this, if the light that you're interested in, that went into the material to have interactions, to have absorption, to have scattering, that will be the interactions with which you can characterize your materials. So this light, you will just get back in your detector, will have the same spectral content. It will therefore just be an offset without any information. However, the information that you can get out of it is your surface roughness. So no light going into the materials, but a surface roughness. And this is very important for diagnostics as well. Because if your vessel wall or your abdominal cavity wall is slightly elevated and rough, that is usually the thing that there's a problem there. There's a process going on which may not belong there. So the surface topology is something you get out of this, like diffuse reflections from the surface, which is a super important diagnostic tool as well. The specular reflections, that's just mirror-like reflections, that is just something you want to get rid of. How can you get rid of your specular reflections? If there's light, that's so you're driving a car, basically, you're looking at some other car and there's a big specular reflections, maybe the light reflected in your eyes. What do? Sunglasses. Polarization. There you go. So you had it, the toolbox, polarization, cross-polarized imaging, meaning that the light with the same polarization direction will be blocked by cross-polarized, and the stuff that loses its polarization direction by scattering will go through, and you get rid of your specular reflection. The surface inhomogeneity depends on your application. If you want to study it, if you want to have some elevated skin, some rough skin, sometimes you see on the skin that there's a little something that does not belong there maybe. It's a bit rough and a bit scruffy. Then you can see it based on your diffuse surface reflections. So that's the information. Now there's a differences in distance as well. So there's a distance which may be different. And this is an example. What's this, you think? If you think about biomedical optics now. So what is it?
Ball.
A ball?
Mm-hmm.
Mushroom.
Ah.
A mushroom, very why mushroom? Very homogeneous material, all kinds of different reflections from different sides. So the intensity is also influenced, not just the spectral content, but the whole intensity is reduced if you're looking more to the sides of this curved object. And it will be the same thing if you were looking to your skin, to your wall of the esophagus, those kind of things. You will have intensity differences which are not disease related, but are just caused by the orientation of your light source in your camera. As you can see here, the intensity is this change as a function of like angle away from the camera, but this is not the information that you want. And if you look at the spectra that you get from all these areas, you can see they're all different. And thinking that you're studying these spectra because you want to see chemical differences, but there are no chemical differences in here. You can see all the different spectra and only caused by geometry differences. So you need to do something to correct this. For that, we very often use a standard normal Variate Transform, which is basically a transformation of the spectrum, weighing it around a certain point in the spectrum so that you correct for intensity difference and standard deviation differences. So how well these images are stretched. So you're correcting basically for the offsets and you're correcting for the intensity in your spectra. So you want to weigh it according to the standard deviation. And you can, so this is the average standard deviation. So if you take every point on your spectrum and subtract the average of that spectrum, then you divide it by the standard deviation. You've normalized the spectrum according to its standard deviation and the average. Then you get some weighted spectrum in which you got rid of the offsets, the intensity differences, and rid of the intensities in your spectrum itself. So here you have some spectrum of glucose, and when you do your trick, they're all on top of each other, while these small differences here indicate chemical changes and no longer geometrical changes. So this is a very useful way of transforming your spectra that you measure on different locations, on different distances, curved surfaces, those kind of things, to bring them back together and just to show only the shape of the spectrum, and in that shape is of course the chemical components. So that's a trick that you use. Just subtract the average, brings it down to the zero line here, and then divide it by the standard deviation. This brings it back to 1 or 2 times the standard deviation, the variation in values that you have in your spectrum. So this is a very useful transform that you can apply to your spectra in order to get rid of all these influences of curvature and surfaces. So that's the scatter effect, and it uses well a scaling factor. Now, if you're interested in concentrations, then you should not do it, because basically you're correcting for the intensity in your spectrum. But your intensity in the spectrum also is a measure of the concentration of a certain component you're looking for. So if you're studying different components, you're not supposed to use this. So every pre-processing step, you throw away some information. In this case, we corrected for intensity differences, which may be due to geometrical differences and curvatures, those kind of things. But with that, we throw away the concentrations of the components you're looking for in your spectrum. So you gain some, you lose some, and that's also with all these pre-processing steps, you need to consider that. Here again, all kinds of variations, and if you apply that spectrum, you will get this. Spectra before, pre-processing steps, and after. And you can see now only the differences that you can see here are due to chemical changes or chemical differences and no longer to geometrical differences. So it really brings these spectra together, and this is now ready for processing. That's the spectroscopy that we do and all the spectroscopy we do in tissue optics, biomedical optics, we need to do some of these corrections because we always have these geometrical problems, which influence the spectra in a way that we don't want to influence them. So we want just to get the chemical information out of these spectra. Clear? Still clear? And then spectral analysis. We need again, as I just explained here, we need some light transport model. And there are many of these models, and usually they describe, it's basically a matter of bookkeeping where the energy goes to. In this case, in the diffuse field case, we had some volume where light was going in and was going out, and part is absorbed, part is scattered out of that volume. So that's described here. But here, in the case of a simple two-layer model, we can also start with a kind of bookkeeping. So where does the light go? There's incident radiation, very easy, you know, your I0 basically. There is radiation absorbed by the blood, in this case. Some is absorbed by the filter paper or the substrate. Light that's going in is also scattered around because of changes in index of refraction or differences in index of refraction between the cells and the fluids between that. So part is scattered out, that's the third energy line basically, and part is scattered by the substrate if we consider this as a two-layered model. So this is basically the energy balance that we have. We use a diffusion model. And once you have the diffusion model as a theory, you know what I'm talking about here, but scattering dominates absorption. Otherwise, we will never have this diffuse field of light in our medium. We have a one-dimensional photon flux, so you have your photon flux in, and it can either go up or down. That's a simplification, of course. We have some diffusion, so there's no directionality anymore when light enters the medium. Then you can start building up the diffuse field that I sketched here. And we don't have the polarization effects, emission effects. In this case, we have this two-layer medium. So what we can then have is like construct a model like this. It's largely derived from the diffusion equation, but you will get that later. And here there are some factors in there which influence our signal. One is the RS, which is basically the substrate reflectance. So if there's something on tissue here, I'm also measuring next to the tissue to see what contribution of the substrate is. Or in case of a two-layer model, if there's a blood stain on this wall, I just measure next to that to see what the reflectance of the substrate is. That's the RS. Then there is the blood stain spectrum compared to some white reference material. And in the A and the B are the S and the K and the A. The A is this again. And the S and the K are the scattering properties and the absorption properties. So what you can see is that the amount of light that will be re-emitted from that two-layer system depends on the scattering and the absorption. This is A is also in the B. And on this RS, which is the influence of the substrate, how much light will come up from that. And that is, of course, if you still remember that drawing, that's the part that goes in deep and then is being reflected from the substrate. So with this system, you can describe, if you measure the RS, you can describe your absorption and scattering properties, if you measure these two. This is something that's typical for the one-dimensional solution of the diffusion or the radiation transport equation. So if we then try to analyze, if we have the mu A and the mu S, we need to know what kind of molecules are responsible for these changes in optical properties. Right? If you're studying a specific process, in this case, aging of blood, we need to know what's responsible for our signals. So what's changing over time. When we're talking about blood and the like the lifeline of the blood, when blood comes out of your tissue, say, I don't know why, but say blood comes out of your skin or from your body, it's fully oxygenated because it's in contact with air. And the affinity for oxygen is of course super high, so it will be fully oxygenated hemoglobin with these nice absorption peaks that we just saw. After a while, it will auto-oxidate. So there will be an oxidation process, and then it will come methemoglobin. If you can look at it in the body, if you have used hemoglobin, so that delivered the oxygen to the organs, to the cells, it will go back to the lungs, it will be fully oxygenated, and at some part will also be oxidized to methemoglobin. Outside of the body or inside of the body, this methemoglobin will be converted back to hemoglobin because this methemoglobin is not able to transport oxygen, so it's not useful for us. So it will be converted back into hemoglobin, so it can again participate in the transport of oxygen. Outside of the body, when it's on the wall, when it's a crime scene, the methemoglobin will turn into hemichrome. And that hemichrome, that is a kind of oxidized form or a denatured protein form of the methemoglobin. So this is an oxygenation, this is an oxidation, and this is a denaturation. The protein just falls apart, basically. And this is something that, if we know this, we can look at the typical spectra of these components and see if we can find it back when we do that measurement on the blood stain. So we assume that the absorption coefficient that we measure is caused by some concentration of oxyhemoglobin, methemoglobin, and hemichrome. That's the assumption then, if we measure some blood stain. Part of the oxyhemoglobin will be converted to methemoglobin, part of the methemoglobin will be converted to hemichrome. So these three components must be present, and then we can say it's blood. Then we also assume some scattering. In the case of our red blood cells, we see this strong wavelength dependency again, that we also take into account in our model. So this is what we have here. This is our equation, light transport or diffusion equation, approximation. This is the conversion from these parameters to something that we can work with, the SNK, so that we get the absorption and scattering coefficients. Scattering coefficients, we can assume that they look like something like very strongly wavelength dependent. The absorption coefficients, if we know that, we can extract these three. Make sense? Totally makes sense. So by measuring on the blood stain, next to the blood stain, we can derive the amounts of these reaction products, basically. Here again, schematically, measure the blood stain in some wavelength range. In this case, we know that the optical properties are very different for these three components in the visible wavelength range. So we measure between 550 and 800. We measure next to the blood stain on the wall or on the skin, healthy skin. Then we get the absorption profile or the absorption spectrum. Then we do some fit of our known spectra to the measured spectra. Then we can see how much of each component is in there. And then we can just calculate things first. But we have to always look at the animation at the pre-processing step. So that's the standard normal variant. Just to correct for anything that we don't want to have in our spectra. We only want spectra to be influenced by the optical properties of the components, the amounts of components, the relation between these components, and not so much by curvature, by geometry, those kind of things. So this is basically the flow chart of the whole technique, of a typical technique. It's not only for blood stains, but this is also for tumor imaging and those kind of things that you can have there. Clear? Any questions? We'll want to run out and get one of these free boxes of chips, right? So forensic applications, some of these forensic applications where we can apply these techniques. That's first. well, these are all like own body materials, like fingerprints. They're highly fluorescent. I think there are many proteins in there that are fluorescent. The bruise we've just seen. And here the contrast is caused by difference in fluorescence properties. Here the difference is caused by difference in absorption of the different components present in the bruise. Here again, fluorescent properties, fluorescence in contrast with the background. These are semen stains on fabrics. So here the contrast is fluorophores. Well, this is a document research. It's also done at the NFI. What's this? I have to think forensically. So what do you see there? What kind of?
I think it's a weapon which has blood on it, and that is because they don't. Because it looks like a.
You're already thinking weapons now. This is just a violent thing. So there's fluorescence here, which is probably something without any large absorption coefficient. So probably some body fluid, probably saliva. You know, this is absorption that you can see here because this is green light. So there's a huge absorption peak, probably blood. This is something, blood and saliva from somebody's mouth. Now you can study them and sample them separately because you use these two phenomena. Where part of this is fluorescence, part of it is absorbing.
But how did you get like the line then? I don't see.
This line.
No. Like the line, yeah.
This line.
How do you get that if you're like?
Yeah, that was the mouth. It was this line there.
Oh, okay. Okay, yeah. Okay.
So forensic applications. This is part of the, medical optics, biomedical optics, the forensic medicine. It's a very large part of the forensic science. We apply, like we do here with the techniques, we apply it for forensic context. It was first recognized as a specialty early in the 19th century. The primary tool, of course, is autopsy. It's basically looking inside body, what happened there, what's the cause of death. And forensic medicine usually is about the identification of the death and the cause of death. And sometimes the time of death, if they're not too long dead. So they look at the temperature that goes down over time when you're dead. And they have some correlation with the temperature with the time that you're dead. And you can correlate that. But it's forensic medicine, if you look at the weapon, for instance, they examine the wound. They can give you information about the type of wound, the distance the shot was fired at, those kind of things, the angle of fire. They use radiology, so that's radiological imaging to see the trajectory of the bullet inside the body, to see whether it was really the bullet that killed that person or if there was some disease, underlying disease. Maybe you get scared or something and the bullet was not the element that killed that person, but some other things. So that's basically forensic medicine. There's forensic first-line medicine. These forensic physicians, they go often to crime scenes when there is suspicion of a non-natural death. You have to ask for a forensic physician to study the body, to give out a non-natural death. That's first line, usually also checking out suicides and those kind of things. And then second line is more the radiology and the pathology. After the first examination and the taking traces of the body, they go to the second line. That's usually radiology or outside examination of wounds and entry holes and exit holes and those kind of things. And that's a large part for which we also can apply our techniques that we use in regular diagnostics, as I just showed. So, well, we're going to use spectroscopy for that. For instance, here, bruises, very important, as I just said. This is more also forensic first line application. Whenever there's a person with a bruise, either caused by domestic violence or child abuse or violence in the street or anything, They go to the police, and the police send them to the community health service, the GGD, where there are forensic physicians that look at their wounds, that note down their medical history, medicine use, circumstances, alcohol use at that moment, drug use, and they note it down. That will go into the police file, and they illustrate the wounds and the underlying, well, the situation that was there when these wounds were caused. And this, of course, helps to confirm or reject statements of a victim or statements of a possible suspect. So you need to do this documentation very carefully, because it's so important in these cases that these wounds are recognized and in the files. Because otherwise, if I say I'm hit but I don't have any bruise here, it's not a very strong story compared to when you have a good image with maybe also the outline and the shape of it. So in the community health service, there are a lot of these bruises, especially after Friday, Saturday night. People come in with a lot of violence in the streets, but usually also throughout the week there's domestic violence, child abuse, those kind of things. And our task first was to say something. Can we image the bruise better for the police files? Can we confirm their story? Can we maybe get a shape out of these bruises to see what hit them? And the second question was, can we date these bruises with spectroscopy? Well, now we know how things work. So what we're looking for is the component that is involved in the process. And in our case, it's bilirubin and hemoglobin, right? So we are looking at the absorption peaks of hemoglobin and bilirubin, and they're at the blue peak, a large blue peak, or a green light. And that's where you can find differences, because the surrounding tissue will not absorb so much green or blue compared to the parts where there's more blood. So you get contrasts. This is contrast we need. So here you can see a blue bruise, or basically an arm illuminated by blue light. What can you say then about the bruise? This one is a deep bruise. Blue. What is long wavelength? Sun, heat, red. So blue is high energy. With blue light, you can get energy in a molecule. You can excite it. You can create a lot of fluorescence. You can create your glow-in-the-dark stars. A lot of light there. That's a lot of energy. The red light is low energy. The disadvantage here of the blue light was, what was it?
Just penetrate very, very deeply.
Now, so you're basically looking or interrogating here very superficial volume, which can be a problem if you want to study deeper wounds, if there's more force or some other plexus is damaged. So here you know that I get some contrast, it's not very deep, so maybe I will switch to green light as well here. But you get less absorption, but you can look deeper. So it's a kind of trade-off. A lot of contrast, but if the bruise is not at that, it's not so superficial, then you will lose it and you will not see it. And you can switch to green light in this case. So here you can also see the skin color is very difficult in daily practice. If you want to make good photographs, it's very hard to see the bruises and especially the shape of the bruises on darker skins. Now, when you selectively look at these components that are important in the process, you can much better see the shape, size of the bruise. So that's something that we've also been working on a lot, to just document these bruises very accurately. And then we can move to longer wavelength. Because also the melanin that is more present here, that's also highly absorbing at shorter wavelengths compared to longer wavelengths. So if you want to get away a bit from the absorption of melanin, absorption of the first layer in the skin, you're moving to higher wavelengths, to longer wavelengths, and suddenly you start to see these bruises appear. If you would look at this with white light, blurred by the reflections, there's nothing much to see. Here again, a wound. Do you see anything there? There's a victim, big story.
A little bit of coloration along the edges.
Here.
Yeah.
That's the curvature.
Yeah.
Now, if you illuminate such an area with 450 nanometers.
Yeah.
Jesus.
I have a question.
Yeah.
Will you be posting this presentation on campus?
Yeah, but not with the examples.
Oh. No, because I was wondering, because a lot of other presenters posted their presentations on campus. They also always post it in the form of a PDF, and then you never get these sort of transitions.
I know. If you have like all the animations there, they will stay on top of each other.
Yeah, they will stay on top of each other, and so you can't see the bottom.
No. Well, you can record it in your mind now.
Yeah.
This is something that clearly shows if you just hit the absorption coefficient of that particular component to the right spot, and this is 450, so just on the flank of this high absorption of blood, will also still be the Rubin. You can see these differences in absorption, and this is quite superficial, 450. There is autofluorescence from the surrounding skin, so long exposure times here. And here is darker area, will give you the idea of the bite wound, which was indeed the story. And there's another thing, UV light. So you're going even to shorter wavelengths, which will not penetrate the skin at all, well, very little, a couple of hundred microns. Will give you an image like this, here in the teeth. Now, what are we looking at here?
Another bite mark?
True. Why do I see it?
Because I see the white color, this sort of ring of white, slightly whiter coloration along the, as well as the dark spots just within that. You see the dark spots, but outside of those dark spots, you see sort of a ring of white.
Yeah. Yeah, there can also be. They may also fool you, of course, but in this case it's true. And here we're not looking at the absorption. But what's this? What are we looking? What kind of optical phenomenon are we looking at?
Reflection.
Yeah. Yeah. Yeah, you should read it. So what are we looking at here?
The picture.
True. No idea. What was the other thing that we could observe in almost every molecule in our body?
Fluorescence.
Fluorescence. Skin is highly fluorescent, and most of that comes from the more structural molecules. So collagen, elastin. Collagen, we have a lot in our skin. Don't believe that you can bring collagen in your skin with some cream or something. But the collagen is something that's very present in our skin, gives firmness, gives flexibility, and there's elastin. They all have very high fluorescent properties. And if there's a trauma, these collagen chains, they start cross-linking. And that will change the fluorescence. So that's what you see here. This is a trauma, big impact on these very delicate structures. They start cross-linking, and then you can see a change in fluorescence. You will not see this on normal skin. You will not see any change in the skin. If you study this with fluorescence, you can see these exact differences where there was more pressure on the skin. That's the UV. So another thing that you can use here. So, well, we can use these in forensics for high contrast imaging. This is something that we spent a year or more than a year at the Community Health Service at the Letselspreekuur. So that part of the day where people could come in with wounds. Letselspreekuur. And then, I mean, the physicians were, so we looked at all these wounds, see if we can optimally use these wounds, see what we could do with different light sources, with different wavelengths, with different skin colors, those kind of things, how we could best optimize contrasts. and then we went to the spectral imaging part. So this is something that it's all in your toolbox. You can calculate, you know this, how this works. It's not your fuck. So can we do more? If you can really measure this wound healing stuff, then we can maybe see the age of this wound. Well, so if you go back to the bruises again, child abuse, big problem. It's increasing, or at least the amount of cases that will be recognized, or where there's a suspicion that increases rapidly. And there are actually no ways that you can measure anything on these wounds or bruises today. So you can look at the behavior. If a child is scared, the interaction between the parents and the children. Say a child is presented to the pediatric doctor. Maybe there's some unconvincing explanation of how these wounds got there, because they have to be consistent with your developmental skills. If you just start to walk, you have wounds or bruises at different locations on your body, as we all know. Then when you can just fall over, or when you're clumsy, you have bruises at typical preferred locations compared to when you're skillfully moving through the world. But also when a child cannot roll over yet, it's very, some locations are very rare if people to get bruises. So location is also true. And there was some idea of how that they could estimate the age of the bruise based on the color. But that's not true, of course. Is it? Why is a bruise called in Dutch a blauwe plek?
Because it turns blue after a while.
Why?
Because of it's the breakdown of the hemoglobin after a certain period within the body.
What's blue?
Is it blue because of scattering? Tissue.
And why is then blue? Why is then, if you look at these, did you have this example or not?
The blue veins.
Yeah.
In the body. Is that because of the blue light gets scattered more than all the other wavelengths?
Why do you see it blue then?
Because of the light that is scattered more gets reflected more, and so reaches your detector more, and so it appears to be more blue than any other color, so it appears blue.
Where are the other colors?
They are still there, but to a lesser extent because they get scattered less. That's the way it was explained to us.
Yeah, why is the sky blue?
For the process that I just explained.
No. Yeah, what's then the difference between normal skin and the skin with a vessel?
Many more things with which it can scatter.
Key is missing, right? So why is this vessel green or blue, depending on the thickness of your skin? That's correct. Why, if it's very cold, it's
Because of the lack of blood.
what's happening there?
Blood is being retracted, and so the red color dominates less.
Temperature is a good one, but optically, what's happening there? What's happening? So there's a vessel here that's very deep. You don't see it. And it's getting up more, higher, and it's green. Then it goes up more, and it's blue. And then it goes up more, and then it's red. There are more and more structures in there that makes scattering harder and difficult and strange. If you have these spider veins, for instance, in your nose or anything, I don't know, and they're very red, they're totally on top of the surface. They're very red, red nose. If it goes slightly deeper, they're bluish. They're still a little bit more deeper, thicker skin, it's green. If you have greener, bluish, if it gets deeper, here come. What's happening here? No idea?
Can I do a suggestion?
You already did, yes?
The overtaking, perhaps it's because at different depths, different processes dominate in the color in the color that is primarily reflected back. So because at the lowest depths, so close to the skin, the color of the blood really dominates. Whereas if it gets lower, it turns blue because then the scattering process dominates more, and so because the blue light gets scattered most of all, it appears to be blue. And get deeper, because the blue light cannot penetrate as deeply into the skin as green light. It's mainly the green light that gets reflected back. It's just a suggestion. I don't know.
Because your eye is more sensitive to the green light, so the deeper you go, you see the green light.
Yeah, well, that has something to do with middle deep veins.
And it's also because of the wavelength of the color.
Yeah.
Yes. Now I have to connect it all.
Yeah, just connect it all. Just try to get the whole picture there. Look at these vessels going down in depth, and
so the energy, the depth, the wavelength,
yeah,
and the way you see the colors.
yeah.
And if you
It all
combine it
combined.
all.
And then put it in the blender, and then you get your answer. That's
Yeah,
good.
exactly.
But so there's a vessel here. All the light will go in, blue light, the green light, red light, and your skin will just be influenced by, blood is still the main absorber, by the microcirculation, smaller vessels that are still here. And the loops. Then a vessel is here, slightly higher. Then the blue light will go in. And the green white light will go in. The red light will go in. Although the absorption coefficient is not so high of the blood there, of red, because it's a low, it will be most influenced by this very large amount of blood in such a vessel. It's very compact, it's very highly scattering, it's very highly absorbing, it's still even. So red will sort of disappear because of the structure here. If the vessel is here, then the blue light will go out, the green light will be absorbed, the red light absorbed. So that is blue. Here it's green, by the way, because the red light disappeared and the green and blue will come out almost like here, but eye is much more sensitive to the green, that's the eye connection. And here the green and the red will disappear and the blue light will just come out, so here the vessel is blue. And here all the colors will go in and will be absorbed according to the absorption spectrum of blood. So the red will be absorbed less, the green will be absorbed quite highly, and the blue will totally be absorbed. So here only the red is with some factor being able to escape. Here the vessel is red. So here's blue, here's green, here's gone, basically. So if you have a bruise and you try to, the lips thing is of course because then the microcirculation closes and then the blood will go down, the plexus will go down. So here it will go from normal vessels very close to the surface, which appeared red, it will go down, and there only the blue is able to scatter around freely, and this will turn more blue like this color. And if the circulation would close, we would suddenly have green lips, or no lips. No. Anyway, so the color is something that is very much depending on the depth. And the skin has the other property that it has a color, melanin, so there can also be a filter on top of it. So the color is not a very good parameter to use where you look at the age of the bruise. Now, if you look at the protocol from the child abuse team at the MS Children's Hospital in the AMC, you can see that they also used colors. They're not doing that anymore. But here, blue-purple was 2 to 5 days, and green 5 to 7, and brown 10 to 14, and 2 to 4 weeks, no evidence. So that's very vague. And when you compare to other literature, for instance, in the color yellow, then you can see sometimes 1 week, the article, a scientific article published, peer reviewed and everything. And here 8 to 10 days, and have to do it with the mouse, of course. So here it is, it's 10 days, here it's 2 weeks, here again it's 1 week. So there you go, there's no really objective way of taking the age of the bruise, of course. So based on visual inspection, it's not possible. That's the main messages. So we went to use, again, took the same approach that we showed before, measure this, measure that, and do some pre-processing, do the processing, and then get the age of the bruise. We set out to do that. We did a lot of, we put a lot of efforts in that. A method for aging the bruises, combining the spectral imaging with some mathematical model. At first we had to understand the formation and the healing of processes in the bruise, because strangely enough, it was very much unknown what happened in a bruise. I mean, the doctors, they're interested in why you would get bruises, the cause, maybe there are more bruises than you would expect, but how such a thing heals, nobody really knew. Then we had to measure a lot of bruises and identify the typical processes, which we can correlate to the age by performing spectral measurements and then make some computer model. So this is what we did. We already know that the color of the bruise is highly influenced by depth. That's what we've just seen. Even by size, the blood pool, because there's a different light propagation around the bruise as well. Shape, density of the skin, skin color, and of course the observer and the light source used and those kind of things. And here's what we started with, some model that they did in Norway, in the group of Lars Swasand. That's really one of the founders of the Biomedical Optics. How do you say that? Fuck. Spatial, well, yeah. One of the real founders of the field. Yeah, field. Thought if I say it like a couple of times, somebody will jump in and save me. So that's super nice. And we kind of looked at this and thought, hey, maybe this is important for child abuse, because in the AMC we have a large child abuse team that looks at babies, very multidisciplinary. There are nurses in there, there's a radiologist in there, there are pediatric doctors, of course, in there. There are people really specialized in child abuse. So we asked them, is this useful for you guys if we can estimate the age of the bruise? We started with this, and then we got some subsidy to progress it further. So first we did some fiber-based spectroscopy using just an optical fiber to get the light in, light out. Then we got the spectrum, and here you can see typical spectrum of blood. We did many subjects here, and it was a mess basically. Yeah.
But how do you validate this? Because there's no way that the parents of the kid will say, oh yeah, I did this to my kid 5 days ago or something.
No, we do the validation in non-abused people. So people that are injured from a car accident, from violence in the street, from anything that has a good record of time.
And is that, but then we obviously ask that to adults, but how do you do that with children?
With children, you ask it to the adults again, because they're in the hospital due to some accident or incident or not child abused. So you specifically have to state then that, I mean, we're not looking for child abuse here, we're just validating a method which may help in a later phase, after validation, to identify child abuse. Yeah, no, it's very strange what these doctors are able to do, but it's for each person it's different. It's not only the depth, it's not only the thickness of your skin, it's not only the composition, but it's also the activity and how fast the bruise heals. That's also different between different persons. If you're younger, your bruise heals much faster compared to when you're somewhat older. If you have a lot of abuse, if you're hit a lot or do some martial arts stuff, then your bruise heals much faster compared to when you have a bruise once in a while. Because there's a total upregulation of your system. Yeah.
Is it also like male and female difference in that?
Yeah, there is a small difference. Yeah, yeah, and that's there's a composition aspect as well, because if you have a more loose skin, or yeah, the loose skin, then your light will of your blood, your hemoglobin that will be freed from your vessels will diffuse much faster, exposing a larger surface, and then the conversion is faster because there's a lot more enzymes that will convert the hemoglobin to the bilirubin. Yeah. So if it's more compact, it will take a longer time because there's a limited amount of enzymes. It's an enzyme-controlled reaction, conversion of hemoglobin to bilirubin. So there's a limited amount of capacity to convert that, and if it's spread out more, it's faster. So that's also a difference. And what we did as physicists, we tried to make a bruise model, a very schematic skin model. Do you know anything about finite element modeling? So if you want to calculate.
No, I remember.
Yeah, it can be. Little cubes.
Yeah.
Yeah. So you explain it.
Let's just not do that.
So when you have a very complex, say you want to have an analytical solution of blood pool that is freed and that diffuses through the skin in all kinds of shapes. That's impossible to solve, right? There's no solution for that. You don't even know what the boundary conditions are. There's no one solution for the blood that flows out of the vessel into the skin. So what you can do then is to chop up the whole problem in thousands and thousands of very little problems that you can solve. So here we just chop up the whole bruise in these little cubes. And we fill each of these cubes with either blood or tissue. So in that way we can describe the bruise in any shape. And then we just take one small time step and see how much of this blood will go to the neighboring cube, and that neighboring cube, and that neighboring cube, and that neighboring cube, to see if there's some diffusion in it 1 second. You just have to consider 2 cubes, 2 neighboring cubes. And the amount of blood that's transported from this cube to this cube depends on the diffusivity of your blood through porous material like skin. So that's easy to solve because there's a concentration difference. There's a kind of resistance to go from here to here. You know all that. So you can exactly calculate how much goes from this cube to this cube. Now if you do that just for all the cubes and see if there's a blood cube or a tissue cube or a blood cube and a tissue cube, you can do any shape and you can second after second, you can calculate how much blood will go to the neighboring cubes. So you've solved that super complex big problem, you chopped it up in all solvable problems, and this is the finite element method. Now it all comes back. So we described several things here. That's the diffusion outward, that's the diffusion to the other layers, and there's the conversion of hemoglobin into bilirubin. And that's Michaelis-Menten enzyme-controlled kinetics. And then there's some sort of clearance that you can also simulate, because you can just have this. So here's blood, goes to another cube, part is converted to bilirubin, you just follow the bilirubin, and at some point you just let it disappear. So you can basically simulate the whole process in this bruise with this finite element model. And this is what we used to solve it. Here are some parameters in the model. The conductivity, so how easy goes one fluid from one cube to the other. There's the hydraulic conductivity, there's also the diffusivities, how easy things flow around. The affinity of the enzymes to convert hemoglobin into bilirubin, the maximum speed of conversion, this is the amount of enzymes in the skin. So a lot of factors here. Some can you get from the literature, some you have to fit in your model, some you can measure. So what we did, we measured the bruise in a patient or a volunteer or somebody with a bruise. We put it in this model and then we just let it diffuse and convert in time. So we actually simulated the healing process of the bruise in our model. And what we then do is we measure at several time points in this person how well our simulations match the real thing, and if not, we're going to adjust all these parameters that you just see. just a little bit higher diffusivity maybe, a little bit this, a little bit that, until our simulations match the measurements. And then we know for that particular person, we have the right diffusivity, the right enzyme activity, the right anything. So we can calculate it back to t is 0. So we have to do a couple of measurements in time on that person. With these measurements, we're optimizing our model so that it matches that particular person with that type of skin and activity. And then we can calculate it back to t is 0. That's it. So we measure the concentration of hemoglobin in the skin, and we do the initial guess, we do the simulations. If they match, we're done. We can calculate when the whole process started. If not, we go back, adjust these parameters, slightly higher conductivity, slightly higher activity, a new simulation until things match. Cool, huh? That's leuk. So here, you have to first get the bruise from images, and you can do spectral images, of course, for that. And this is what you have to bring into the model. Measure these areas, see how things are different. Here you can see the blood absorption, here you see blood absorption, plus a little bit of bilirubin. And here things disappeared completely into the third component. So this is what we do. We measure with spectral imaging, we correct for the curvature, pre-processing step, standard normal variate kind of things. Then we measure a spectrum. Then we see how much hemoglobin is in there, how much bilirubin is in there. And we get that for all the points in our image, so we can make maps, like hemoglobin maps, bilirubin maps, melanin maps. And then we see if our model predicts the same kinetics of healing over time. If we don't have a match, then we just adjust the parameters until we have correct simulation of the bruise. Since we started at, say, 20 hours or 2 days, and when we start doing time measurements, we use these time points to optimize our model. If we have these parameters correct, we know at what time this process must have been started. And this is the T0, the moment that this person was hit. Here again, image processing. This is what you get. Then you do some thresholding with elevated areas. This is then the hemoglobin. Get rid of all the noise, and then you get these areas. And again, bring it in the model. Look how it behaves over time and compare it. So we did a lot of these kind of things. And what you get is curves like this when we started at 20 hours. And here we did a lot of measurements. This is the hemoglobin, this is the bilirubin. And the lines are our model, our final set of model parameters. You can see they just match quite accurately the lines, the little measurement points. And from this, we can calculate it back to T0. That was about 20 minutes or 30 minutes error. 6-hour error when Bruce was 2.2 days old. We had some 9-hour error with a 5 days old Bruce. Yeah.
So the bruise is specifically for a specific spot for one person. So
yeah.
Use the model
So every time you optimize your model to match the enzyme activity, the diffusivities, all these parameters.
But also like for one person in a specific area.
That's different. Yeah, that's much different compared to the thinner locations. Or the eye, if you see the loose skin, it sags down sometimes. Even when you're old, it's like totally blue. So that really depends on the location on your body and age and everything. Also the impact. So you have to optimize the model for every bruise that you examine, basically.
But then for kids, the location is normally not coherent with what you would expect, right? So, and you're just saying that the location also depends on how a bruise evolves. But then with your sample size, that's what you can expect. For example, if you have an accident, that's also what you can expect, right? So how do you then calculate for that location change?
Well, we still do the same procedure,
Yeah.
only we have to do it. We take like 3 time points. So the kids come in, we take 3 time points at half a day, and 1.5 day, because you have to be very fast at these kids. Yeah. And then we just let our model optimize until it matches the same. It's the same principle.
Well, yeah, I get it's the same principle, but with the location, like you will never know from like.
No, but the whole process is independent of location because it just optimizes all the parameters of a specific location without our knowledge, without us having to put in a priori knowledge.
But would you not get a bigger error then? When you like change it from location to location?
And now for each location, what will give us a different error is if the progress of the bruise is slower.
Oh, okay, only if it's slower.
If it's slower with older people or some other locations, maybe on the back, then there's little change in a certain time period. So if you measure a set of parameters, it's not very specific for one period, but for a longer period. In kids, that change is very fast. It goes up, down, gone. So for each time point, you have a very specific set of hemoglobin, bilirubin parameters. So you can do a much more accurate estimation of the time of infliction compared to the long process in older people. That's a big difference. And it's also something that we teach to the pediatric child physicians in that order or another order, because you have to record your traces, your bruises, your wounds very fast. Because we had a child at the child abuse, well, no, at the children's surgery department in the AMC. And we ran down to get the equipment, and then half the bruise was already solved. It was gone, it was healed. So fast sometimes that it's great that you get a very accurate thing with time estimation, but it's hard to get a good view on the traces that are on the body. So that's the bruise development and the physiological parameters. We now have used all this toolbox that you have, light transport and those kind of things, to work on this problem and solve it. And but we're still doing now the validation at the Emma Children's Hospital, where the kids come in after accidents, incidents, or undergo surgery, and we exactly know what happened to them. And we do our validation still on there because it's so. Well, you have to be so critical before you introduce such a method into practice, because the things that you're saying about the events, they can have big consequences, of course, for the people coming in. So that's something that we also have to deal with. Short break, and then the last part of the crime scenes. And then we.
Oh, minus it. It's like that for it has its minus
Again, recording, so localization of your specific interesting trace, your chemical analysis, and the forensic questions when you find traces like this is it blood, whose blood it is, how did it get there, when did it get there, and two of those, so how did it get there? Of course, we cannot answer with spectroscopy. We can answer when did it get there. Whose blood it is, that's DNA stuff, that's also not our thing. But is it blood? Of course, we can again examine the stain with spectroscopy and see if our reflection spectrum is something that we expect from blood. So here you can see some other things in the body. It went to bilirubin. Here the blood goes from oxyhemoglobin to methemoglobin, and from methemoglobin to hemichrome. So again, there's the hemoglobin, oxygenated, oxidated, rusts basically. The iron goes from 2+ to 3+. And here there's a denaturation, hemichrome, and that's the other component. And these three have very different spectra in the visible range. So in the part that we can see, from 450 to 750, we have all these different spectra. Something we can also observe with our eyes if we look at the bloodstain, which is old, something, I don't know if you've ever seen that, if not, you don't have to say it, but anyway, if there's a bloodstain, it turns slowly into a dark brown kind of stain. And that's that conversion. And if you measure that, you see this slope change a bit like the arm of a clock, which means that you have something here from which you can develop a method that is very robust and with which you can correlate the spectra with the chemical changes over time. And there's no other method that can be used to give a date or some age to your traces, nowhere in forensics. So this is a very nice trick to study that. And indeed, if you've done your pre-processing, if you've done your calibration and your pre-processing, then you get these spectra, again, standard normal variate, because they're weighted around 0 here. This is standard deviation. So here the spectra with the 2 peaks, which are typically of oxyhemoglobin, and there's something happening here, which is the methemoglobin. You can see just the chemical changes in there. In reality, it's a bit more difficult, more complex, but we just look at this simple process there on top. If you measure that just on the crime scene, you can see 1 hour, there's this hemoglobin spectrum. In this case, it's not the absorption spectrum, but the reflectance spectrum, so it's the other way around. High absorption, low reflectance. So the reflectance spectrum, 2 peaks here again of oxyhemoglobin. Going to 1 day, you can see this absorption peak or reflection dip come in. This one here. So here the 2 peaks of oxyhemoglobin, here the reflection peak or the reflection dip, absorption peak of methemoglobin, and it goes on in time to finally end up in a spectrum, which is most of the material that you find there is hemichrome, which is a bit non-specific. So this is a nice chemical process that you can follow. And if you can measure that on the crime scene and correlate it with the relative concentrations of the components, then you have some aging method. So we looked at stains up to 2 years old to see if something would change there. How long do you think things are still changing in this bruise? If you have some blood on the wall, on the floor, on the ceiling, I don't know, how long do you think we can still see changes there? Usually the change in color, that's in a couple of days, it's there, right, for your eyes.
In a month.
Months, maybe, yeah.
Is there a way we can know this, or is it just a pure guess? Yes.
It helps you to freely estimate these kind of things without having your fixed theoretical underpinning. It's a bit of a freestyling. Sorry? No, that's not usable in forensic relevant times. So the coagulation factor or changes in DNA, RNA, they're explored as dating methods. But if you find a dried bloodstain, there's no way that you can determine the time of deposition. If you have something in the cuvette, which you can correlate to some coagulation cascade or something, then you can do some estimate, but this is a very short time. So that's something that's. And here, if you look at the 600 days, so 2 years, you can still see changes in the bloodstain if they're deposited somewhere. And you can see that whole chemical process in time, where there's the oxyhemoglobin going down, there's the methemoglobin going up and down, so that's this product in between. And then you can see the hemichrome going up to finally be the end product after 2 years. And if you can now see that at each moment in time you have a very specific combination of the three. So if you can measure this combination, you can put it on this bar, on this time range, and then estimate the time of death. But again, with the bruises, the changes in the beginning are much faster. So a certain combination is much more specific for a certain time point. And here at the end, changes are much slower. So the time resolution, the accuracy with which you can do your estimation, gets pretty worse at the end. But still, if the question is it from a month ago or half a year ago, can easily be answered by this curve. So again, we used spectral imaging, be correct, do pre-processing for differences in distance. We do the SNVs, we do the all the spectral processing using light transport models and fitting, and then you end up with the different concentrations. And then from these concentrations, you go to a timeline. Same thing as the bruises. We don't have the difficult skin on top of our problem here. So it's much simpler. But the thing here is that the environmental circumstances are very variable. So where in a bruise, the physiological circumstances are very well controlled. Temperature is very well controlled. All the values, pH and things are in certain limits because that's how you function. When you have a blood stain outside, it can be hot, can be warm, can be wet, can be anything. So the reaction rates, these rates, very much depend on these environmental circumstances. So we need to take all these into account when we design our models to do something of the aging. But the cool thing is that we just by using the same method that we use in the clinic, that we were able to design this method, which is the only method right now that can do something with blood. So this is all based on reflection spectroscopy. Again, we're looking at these components because they absorb in the physical in the visible spectrum. We can also look at these components in the near infrared spectrum. So we go longer wavelengths, or the short wave infrared spectrum, or the near infrared spectrum. And then we look more at vibration levels of molecules and how they change over time. But the other thing is fluorescence. And besides just looking at fluorescence, as we do on the crime scene to find biological traces, semen, saliva, urine, those kind of things, we can also do spectroscopy on them and then look how it changes over time. So Annemiek started with that, and Nihat is now a PhD student on the project. But if you do the excitation of a protein-rich fluid, can be semen, can be fingerprints, saliva, then you get two peaks basically with two excitation wavelengths. So this is UV excited, you get this protein peak, this very high peak, which is there in fresh material. And over time, these proteins are converted into some fluorescent oxidation products, FOX. And that's something that's just an aging process, like it was in the bloodstain. With fluorescence, you just have to measure protein peak first and then measure the second peak with another excitation wavelength. And if you do that over time, you get something like this, where you have a fresh one, a lot of proteins here, and this is tryptophan, which fluoresces with a low fluorescent oxidation product peak. 1 week, you can see this go down, more of the fluorescent oxidation products are formed, goes down, goes higher, this one goes down, and after 10 weeks, it's higher. So here again, you have a very robust mechanism that you can measure, more robust chemical change that you can measure using just the same fluorescent methods that you also use in vivo on patients. Just different products, excitation. And so if you then take a protein FOX ratio, where this is high in the beginning, and this is very low, so very high ratio. This goes down, this goes up, so this ratio goes down. When you put all these points, these ratio points in the timeline, you get something like this. Then you can design a function through that. That if you just measure some of these points, you can fit this function through these points, and when it goes through the intercept, that's your T0. So when you find some fingerprint, you measure these two fluorescence peaks, take a ratio at different time points, and then again fit it back to T0. And this is the same thing, same trick, using fluorescence, not absorption this time, to also get this very nice result. And here it's in 15 days, you can see these points with error bars. But again, that's something that was discussed. What is the accuracy that you need in a forensic practice? That depends on the forensic question. Sometimes it's like, is it yesterday or the week before that? Or is it from yesterday or the day before that or after that? So it really depends on what's asked, which question goes with which scenario. And that's the thing we try to answer with these techniques. And here's semen, very important in more sexual crimes, where of course this person will say it's my semen, that I had a relation a week ago or something, and it's no relation with this crime at all, or I just spent the night there and I don't know how this happened. And then again, the aging is of crucial importance. We can get this trace, we can get the DNA from that, but if we cannot link it to the event, then it's useless, basically. So here we looked at the same thing, semen, having the same kind of behavior. And when you measure these points here, you can fit it, the line through there, and then you can estimate the, this is tumor age versus estimated age. You can nicely see that there's a correlation there, which needs a lot of refinement, but again, depending on the forensic question. Was it like from last night or was it from last week? These are questions, typical questions that we get in forensic practice. And this is, of course, super important for the victims to have a story and to be able to confirm stories or refute statements from others. Yeah, so I've talked way too long about these applications. And so there's some material about fluorescence detection and photodynamic therapy, which takes another 2 hours. I will not do it to you because I'm only sending. So here I will just put these slides on the slides that you can go through it. It's like very simple principle. Thing is, you have the light source. It's like fluorescence, like making things fluoresce. So you have your excitation source, usually blue UV light, high energy light. You shine on the target, and you block your excitation light with a filter from your observer, and you just observe the fluorescence that comes out of it. That's the whole principle. Now we've got some tricks to calculate how much light is reached, or will reach the target. And then how much light will escape from the target to our detector, and that's all light transport. Not considering time and my amount of talking, I'll quit here and just ask you if you have questions or any question or questions at all or anything. No? You all go out to the spa and get collect your free box of food. Yeah. Any questions? Yeah.
Maybe for the exam. Is this exam material like? Are there some questions from you in the exam? In the model? From these slides.
Not so much from these slides, no. What I've seen, but it's all up to Dirk, of course.
Yeah.
So he will determine what will be in the exam. Is it more that you can understand these processes that are in there? Understand what happens if you change wavelength? That you understand if you want to study a certain process, what kind of phenomenon do you need to look at? Is it absorption? Is it fluorescence? And how important is the wavelength selection for that? What's the penetration depth of something? So there are multiple things that are not so factual, but more to understand the general concept. And that is something that I want to get in there somehow. But this is something that helps you do the translation from this super theoretical toolbox to some application. That is what I was hoping to show you. That everything that you learned in scattering, absorption, all these small changes that we can measure, and how then to bring these measurements into answers that the end user wants. So is this a tumor or not? Or what's the oxygenation? Or what's the age of a trace or of a bruise? Those kind of things. And that is all concepts. It's nothing new. I just basically told you nothing new here, right? It's just a matter of application. And that's hard for a lot of students to do the translation, because you can list tables and you can just get it all out of your head, just learning all these facts and little details. But then translation, use it as a toolbox that is one level higher. And that's what I would like to see. So conceptual, yes, factual, not so much. Yeah. Okay. I was looking for a slide for my email address. But they're not so much indeed. I thought I was everywhere.
No wonder I missed it.
Yeah, no. Okay. Is that it? No. I thought it was somewhere. But anyway, I'll give you the email address. No.
I did see it somewhere. But
You did it? Yeah.
yeah, I did.
Be the first slide.
Yeah. Amsterdam, USA. So our group usually has many projects ranging from physics to biophysics to fundamental to practical work. And we always have some of these internships, of course, for all levels. Usually we tailor them according to what you want. When you want more work in the lab, do you want to work with body fluids, biological fluids? Do you want to do more measurements, more geophysical measurements, or measurements with cameras and anything? We try to find something there. There's a limited amount, of course, of supervision that we can give you with a good quality. So we limit the amount of internships at our department. But if you are interested, I recommend you not to write to me like, do you have an internship? Period. But I've read this and this, that your group is doing this and this, I'm really interested, I want to go more in that kind of aspect, and I want to study this and this. Do you have an internship? So more like you're really interested in what we're doing, and that it is a kind of conscious choice to come to our group instead of all the other groups. I mean, usually I get a lot of letters like, I need an internship next January, just to give one example. That's it. Yeah, cool. Just go find it somewhere else. If you're really interested in the work that we are doing specifically, and it's not only the work here, forensics, it's also the medical part, please be as specific as possible, because that shows your motivation. And it's basically not for only this internship, but a lot of my colleagues have the same idea. I get maybe 20 per week for internships from outside the country, inside the country. I want to do some things in the group. But usually they're like shot of hail, schot-hagel. So they send out 1,000 letters to all the groups and everything, and my name is double A at the end. So I get most of these. They probably take all the address lists and they send it to everything, but they're usually so unspecific and not even sometimes not in the right field. That they're just so, but just be as specific as possible to show your motivation. Also, if you really want an internship, don't write, oh, hi, do you have internships in your group? Bye, or sincerely yours, I don't know. But don't, that's nothing. That does not show that you're interested in the group, in the work that is being done, in the type of research that's being done, in the applications even. That's also good. But just be as specific as possible when you're applying for internships. Not only for this, but always. And that really separates you from all the tsunami and mailtjes that I get.
Noise.
The noise. Basically, it's all noise. Yeah.
It should be long, right? Like really long emails also.
Oh, that's horrible. No, that is a good point. Just something in between. No, just that where it's just very specific. Well, that's also a thing, but just be also in that first email, be clear about the goal that you have, or why you're specifically interested to send me an email instead of I don't know who. So that's the thing. Just I've seen the work of your group, working in the, I don't know, child abuse, or working on spectroscopy, or working at the tissue optics stuff. Be specific, more specific than that. Working on imaging of tumors in oncology or something like that, or anything. But that really has my interest, and I want to study it. It's like very short, but totally show that you're committed, that you've invested in looking what the group is doing. And That's much more than just, hey, I don't have an internship yet. So be specific about it. And otherwise you will not get a reply. I'll just throw it immediately away. I have to do that because otherwise you get these discussions. Yeah? All right. Well, have fun in the rest of the course. It's well, probably run into you somewhere. Bye.